Hello, this is Year 1 Mechanics for Edexcel, Chapter 11, Example 4. So, Chapter 11 is about variable acceleration, and up till now all of the chapters have looked at constant acceleration and the use of Suvat equations. Now, the key thing to realise is Suvat equations work for constant acceleration. This chapter is about variable acceleration. Therefore, when we're talking variable accelerations, Suvat equations are not going to work anymore. So that's a really key thing, and I've mentioned it before in previous videos, but it's something to look for in questions. You need to be identifying whether the question is talking about variable acceleration or constant acceleration. So moving on from that, we're talking about variable acceleration, but let's just revisit constant acceleration and what it looks like. So here I have a graph for constant acceleration. So what does it mean, constant acceleration? So constant acceleration, if we look at a velocity time graph and we look at the gradient, so here the gradient of that line, that is our acceleration. And it's constant because the gradient is constant. At the top here, this is travelling at a constant speed or constant velocity, so there's no acceleration because the gradient there is zero. I would agree my line may be a little wobbly and perhaps even go up a little bit. And then here again there is a gradient, it's a straight line, so the gradient is constant and it's accelerating again, but this would be a negative acceleration because it's deceleration. So constant acceleration is where our gradient is constant, it's one value. Which moves us to what does variable acceleration look like? Well, if we go to a new diagram, variable acceleration would be a curve. And there is acceleration, but this acceleration is varying. So it's not constant for the whole of for any one, it's not constant for the whole of that acceleration. It's changing. And here you can see that the acceleration is slowly increasing because if you think about the gradient there is less steep than if I found the gradient there. So I've drawn tangents at different points on my curve, and because on the first tangent, which I'm going to call tangent 1, the gradient is less than at tangent 2, we can say the acceleration is increasing on that curve. But how do we find acceleration when it's a curve? We need to find the gradient of a curve. And this pulls back on our core skills, and we all know how to find the gradient of a curve now. And we know the key thing we now need to remember is how to differentiate. So we need your differentiation skills to actually tackle this area of maths. So having realised we needed to differentiate, we're now going to look at how this all links together. So if I wish to find the acceleration, that is equal to differentiating the velocity with respect to time. So if I have an equation for my velocity, then what we're saying is if I differentiate that with respect to time, then I find my acceleration. But what about if I move this on slightly and I think about a displacement time graph? So if I had, for example, S t, again, it can be a curve. And here, if I had a function relating displacement and time, and I differentiated that function that linked displacement and time, my gradient at any point would be equivalent to my velocity. So if I have, just going back through that, if I have a displacement equation, expression, function, and I can differentiate it with respect to time, I'll get my velocity. And if I have a function for velocity and I differentiate it with respect to time, I'll find my acceleration. And putting this together, therefore, if I had my velocity and I've actually found it by differentiating my displacement function, then I can also go and say, well, my acceleration would be the second differential of that function. And this is the key part that you need to know. So if I was going to start my notes now, the first thing I'm going to write is my title, variable acceleration. And I'm also going to write down these because it is really important to understand how the graphs, which are above, and these equations all link. And to fully understand about gradients and linking it to the graphs, and also understanding what you differentiate to find velocity or acceleration. So I pause the video now, make sure you understand all that, think it through, write it all down, and then come back and we'll look at the example. So we're now going to look at the example. And if I take you over here, this example is taken from the book. It is example 4. And to start with, just so that we remember, we need to write down that A is equal to dv by dt. And we also need to remember that that's also the second differential of the displacement. And V is the displacement function differentiated with respect to time. So they are our key notes that we've taken from before. Now let's read the question. A particle P is moving on the x-axis. At time t seconds, the displacement x meters from O is given by x equals t to the power 4, subtract 32t, add 12. Find A, the velocity of P, when t equals 3. So here, x, this is my function, and it's my displacement from O. And I'm asked to find the velocity. Well, I know that from before, I know that if I differentiate the displacement, I will find the velocity. So for part A, velocity is equal to dx by dt. Notice it is dx by dt because the function for displacement is x. So that would be 4t cubed subtract 32. But it says when t equals 3, so when t equals 3, v equals 4 multiplied by 3 cubed subtract 32. Typing that into your calculator, your answer is 76. And I need to go back and just check those units because mustn't forget our units. So it's 76 meters per second. I'll just make that 6 a little bit clearer. That's part A done. So to find the velocity given displacement, I've differentiated. This is my expression now, or my function for the velocity, and when I substitute t equals 3 in, I end up with a value of the velocity at t equals 3. Part B, the value of t for which p is instantaneously at rest. So what does that mean, instantaneously at rest? It means that v equals 0. So therefore, I'm going to go back and look for my velocity function, which I've worked out in the last part, which is that. And I'm going to then say that that must be equal to 0. And from here, I would actually factorise to write that, and t cubed would equal 8, so t equals 2 seconds. So I've answered part B now. Find the value of t for which p is instantaneously at rest. It's instantaneously at rest when t equals 2 seconds. Now part C, it says the acceleration of p when t equals 1.5. I need a function for acceleration. I've got something for velocity, I haven't got something for acceleration. However, if we look back up to here, we know that if we have used a displacement function and differentiated it once to get velocity, the second differential will give me the acceleration. So for part C, if v is equal to this, then acceleration will be the second differential, which will be 12t squared. And when t equals 1.5 seconds, we can say that a equals 12 multiplied by 1.5 squared. And again, you can use your calculator for that part. That's 27 meters per second squared. And that's the question answered. You should now be able to work through the exercise. Good luck.